Right. So now we are at part 2. That is, the claim is that whatever the T is calculated by Prim's algorithm, whatever spanning tree is calculated is the minimum spanning tree. Okay. So the question is, whenever you're choosing an edge, let's say whatever edge you're choosing at whatever time step you're choosing, when is it safe to include an edge in the tree so far? And the question is, how can you be sure that it will not hurt you in the future? So basically, whenever you're choosing that edge, it should be an edge such that you are sure that it is an edge that is present in the minimum spanning tree. So although we don't know the minimum spanning tree when we are running the algorithm, that's why we are running the algorithm. But if we can somehow prove that if you're selecting an edge, this is justified by some properties which guarantee that this edge will be present in the minimum spanning tree, we are golden. So let's go. So what's the let's line some building blocks just like we did in the part one. Here we had the empty cut lemma. We are going to have the cut property. Okay. So consider an edge E and G. Suppose there is a cut AB of G such that E is the cheapest edge crossing the edge, crossing the cut. So the cut property is that edge E must be in the MST. Okay, so here we go. For example, we have this graph G and here are two cuts A, one cut AB of a graph, and there are some edges inside here, some edges inside here, and some edges crossing this cut. So this edge E is the cheapest edge crossing the cut A and B. So what the cut property says is this edge E, if is the cheapest crossing AB, then E must belong to the minimum spanning tree. So the claim is that if I can prove this cut property, let's assume it for the time being that this cut property is true. My claim is that the cut property implies that Prim's algo is correct. Let's see how. If the cut property is true, that means for every cut we are choosing, we are taking the cheapest edge and we are including it in our MST, and that is justified by the cut property. So whenever we are running this algorithm, first of all, we are at the single vertex V and rest all of the vertexes are here. And this is our cut, the single vertex S, which we have initialized. And of all the edges crossing this cut, we're choosing the cheapest one. And by the cut property, this cheapest edge is justified. Okay. So how do we prove the cut property is the question. But before we get to the cut property, I'll just put it out formally. Now, whenever we are running, we know that the Prim's algorithm will running a spanning tree at least. So at every step of the algorithm, we are explicitly adding the cheapest edge of the present cut. And by the cut property, the cheapest edge is the one that should be included in the MST and it will not create any cycles. So, I mean, whatever the spanning tree is getting returned by this particular algorithm will be the minimum spanning tree. But then the question is, what the hell is this cut property? How do we prove this cut property? So let's go. First of all, we are going to assume it's distinct edge costs. Okay, no big deal. So we are going to try to argue that the cut property is right by using an exchange argument. That is, we are going to first of all assume that it is not true. We are going to, it's just a proof by contradiction in fancy terms. So let's see. The cut property is for suppose there is this cut A and B of graph G, and these are the edges crossing this, and E is the cheapest edge. So the cut property says that E must be in the MST of the graph. And by the here I mean it's going to be a unique MST, and that is true if there are distinct edge costs. Okay, we are going to assume that there are distinct edge costs. So let's assume for the time being, cut property is false. What does this mean? This means that for cut A and B of graph G, there are some edges. There is an edge E which is the cheapest one, and there is an edge E star which is not the cheapest one. Now, by if we say that the cut property is false, we say that this edge E is not present in the MST, even though it is the cheapest one crossing the cut A and B. So the idea is that if I can somehow swap E star with E, and after swapping E star with E in the minimum spanning tree, we have decreased the cost. That's the first fact. Cost decreased. So it's definitely a smaller cost tree. But then there's the question, is it a spanning tree? So the exchange argument is if I can somehow find an edge E star which is costlier than E, and even after swapping E and E star, we are able to generate a spanning tree which is of a less cost, then whatever we have assumed about this being the minimum spanning tree is false, and hence our assumption is false, hence the cut property is true. So that's the skeleton, that's the big idea that we're going to try to execute here. So idea is, let's try to exchange E here. This is where the word exchange arguments come from. Exchange E with some other edge, right, with some other edge in T star, which is the minimum spanning tree which contains E star. Basically, let me write that explicitly. T star is MST. T star does not have E. T star has E star, basically. Yeah. So exchange E with some other edge in T star, and if this is still the MST, we have, if this is still not the MST, I'm sorry, if this is still a spanning tree, not the minimum spanning tree, we have a cheaper spanning tree. Hence, MST T star isn't MST. So this is a contradiction in one line. MST, we are calling MST, and then we are saying it's not the MST. So, you know. So question, how to exchange E with edge? How to choose this edge that we are going to exchange with? So let's say we have a graph A and we have a cut. Let's for the argument's sake, we have this. Here is our edge E, here is some edge E prime, and here is some edge F. E is the cheapest one. So CE is less than everything else in this particular cut. And by the cut property, if a graph is connected, that means if our MST is connected, there should be at least one edge crossing A and B, in this particular MST, because it has to be connected. So let's say that edge is F, for example. F is edge present in the MST. So C is a cost of E is less than cost of F. That's for sure because he's the cheapest one. So why not let's just do an exchange, let's wing it. Let's exchange E with F and be prepared for the consequences. So my claim is, my statement is, the resulting graph might not be the spanning tree. And why is that? Let's see. For example, if I have a graph such that this is edge F, this is this is our resulting spanning tree, This is E prime, this is F, and here in the is the E, edge E. Now, right now, this is how the graph looks. This is how our spanning tree looks, Forget about the cut, but this is how it looks, and it's a spanning tree. If I were to go and exchange F with E, this is how our graph will look. This is how it looks. This one is disconnected. So not only is it spanning, it's not even a tree. So this is not going to be necessary that this graph, this exchange with F is going to be a spanning tree. So let's not change it with F. How about we change it with E prime? Okay, that's a question. Let's switch it with E prime. And this is how our graph will look after switching it with E prime. F is going to be as it is. E is going to be like this. And this is going to be like this. So this is a spanning tree. Okay. So if there was such a case that there are two edges crossing this cut, if F is not the one, E prime was the one. So here's the question. Can we always find such an edge, E prime, such that swapping the cheapest one, basically E, such that swapping E does not destroy anything, doesn't destroy anything. So if we are able to find such an edge, we can always swap and it will be a cheaper edge and we'll be able to prove our cut property. This is what we're doing. Let me circle back. We are saying is that we are going to try to assume that the cut property is false and we're going to try to get to a contradiction. So now if ever we are able to find this edge such that swapping does not change anything, we have swapped that edge, it does not change anything, we have reduced it to a cheaper cheaper thing, cheaper minimum, cheaper spanning tree. And if it's a spanning tree and it's cheaper, then it is definitely cheaper than the minimum spanning tree that could have been. But then that's a contradiction because that is not possible to be a minimum spanning tree, and hence our cut property assumption is false, and hence a contradiction. So let's go. So if you're able to find such an edge E prime, so the answer is yes, we are able to find. But how do we prove it? So let's you know when we are in this particular state, when we have a graph looking like this, here is E prime, here is F, and this one was supposed to be E star, or edge E, sorry, our candidate cheapest edge of this particular cut E. Let's just go ahead and add it to the minimum spanning tree. It will not remain a tree, of course, because if it was a tree and we are adding an edge, we have created a cycle for sure in this minimum spanning tree, in this spanning tree, sorry, because it was a spanning tree. uh, uh, our tree, whichever is here, is a spanning tree, and we have added an edge E. That means we have for sure created a cycle. So as soon as we have created a cycle, now we can motivate the choice of the swap edge. By the double crossing lemma, that is, we have proved that for every cycle, if there is a cycle and then there is an edge crossing this cut, there must be another edge crossing. It should ring some bells in your mind. And now the choice of that particular edge presents itself to us in a very beautiful fashion. So let's say we add an edge E, we created a cycle. By the double crossing lemma, there exists another edge crossing cut AB, and that edge is definitely expensive. That is not cheaper than E because E was the cheapest edge. So there we go. Let's just find out whichever edge that is and remove it. And by doing that, we have destroyed the cycle. We have restored its connectivity property, and it's a spanning tree which has a cost less than cost of our original tree, which could have been if there was E prime in it. So by the double crossing lemma, we know that there exists. We know for a cycle C, if one edge crosses the cut, there must be another edge crossing the cut. Here E prime, here E prime. So we swap these edges and still maintain the spanning tree, which is strictly cheaper because cost of E is strictly less than cost of E prime. So this new tree, whichever it is, T, with E swapped with E prime is strictly cheaper than T star. And hence we have a contradiction. So let's circle back. Let's go all the way up. We have a contradiction. We have proven the cut property because we used the cut property is false, which is not true. We reached at a contradiction, and hence if E is the cheapest edge in a particular cut, then E must be in an MST. And because that is how by design our Prim's algorithm is running, Prim's algorithm will always output a correct minimum spanning tree. So this was the key, proving the cut property. And we have done that successfully, I think, by using an exchange argument. So here's the running time analysis for this graph. So if we naively implement from the pseudo code, we have total running time. Naive implementation. We have total big O of n operations for each vertex, and for every vertex we do a order m operations to go through each and every edge and seeing whichever is the cheapest, and hence naive implementation is order m and work. But can we do better? That is the paradigm of a good algorithm designer, that can we do better? And yes, indeed, because we are trying to, get minimum edges at every iteration. Somehow, if we use a data structure, that's only reason of existence is giving us minimum operations, minimum cost things. We're going to do better. And such a data structure exists, which is heap. Heap, as well, you know that heap exists only for giving them for computing minimum fast. That's why heap exists, to give us fast minimum for repeated minimum computations. So instead of going through each and every edge in a brute force manner, we are going to maintain and we're going to, for example, this is our particular frontier. For example, we have a graph. This is what we have encountered till now. This is what we have encountered till now. This is the frontier where all of the edges are outside X. This is X basically. So our heap is going to maintain the set of all of the edges crossing this particular frontier, give us the minimum one, pop that from the heap, include that particular X, and recompute this frontier. Basically, remove this edge and add all of the edges going out of here, out of the newest added vertex, and do a minimum of that repeatedly. So these are a bit of caveats because now we need to support heap delete operations too. But regardless, we can use heaps to fast computations, and we can get it in order of m log n. But then let's get into the details. Let's how are we doing it? So natural idea, we use the heaps to store the edges, extract min again and again. But there are some caveats because every time we extract min, we need to make sure it is the edge which crosses the frontier. So if we use heaps to store vertices like Dijkstra's algorithm, we can get a faster algorithm. But see, first idea was to store edges, store edges. So and at every time calculate edges which cross the frontier, extract min, and then update this particular edges. Now another paradigm of thinking is instead of storing edges, let's store vertices. And like Dijkstra's algorithm, we are going to assign a score to each and every vertex. And whenever we pop a vertex, we are not going to have to worry about it ever again, because including a vertex in our X ensures that it is going to be an X forever and there is no update needed. So this is what we are going to do. This is just an implementation detail. Invariant number one is elements of heap. Invariant of this algorithm is that elements of heap are vertices of V. Invariant number two is for V belonging to V minus X, that is outside the frontier. The key of V is the cheapest edge going from, basically just like the Dijkstra's algorithm, cheapest edge from U to V, where U belongs in X and V was, as we said, outside X. So just like the Dijkstra's algorithm, where we have a frontier and whichever vertex is outside that frontier, we are going to have as its key the minimum distance that it has from the particular edge here. So infinity if no such edge exists. So and whenever we extract that minimum from the heap, we are going to choose the topmost element of the heap and heapify this entire process again, and we will have the vertex which is the minimum one from this particular thing, right? Just remember this, after we are extracting the min in this particular thing, the frontier has changed, and now hence because it has changed, we have to recompute the keys of all elements outside X basically. For all of these vertices, we have to update the vertices. So let's see, let's look at the pseudocode which I've written here. Pseudocode for this heap operations. So when V is added to X for each edge, VW, so that is edge that are incident on V. If W belongs to V minus X, that is W was outside the frontier, delete W from heap, delete W from heap, recompute key W, and reinsert. Right? So here's the idea. And only why are we only looking at the vertex which are incident on V? For example, this is our graph, and this is the one right now with the cheapest edge, and this is it how it's connected to this. So this is our graph. Whenever we are adding this to our particular graph, the only thing that has changed is with respect to this vertex. That means for a vertex that is very far away from this, the cheapest edge, that the key that this vertex has might not depend on this. For example, so what I'm trying to say here is whenever we are adding this vertex V to our set X, we only need to make changes locally around the neighborhood of V, right? Because anything that's far away from V, which is not directly connected to V, does not change at all when we are adding V to when we are adding V to X. So only change for those vertices which are directly connected to V, recompute their keys. It's possible that, for example, this W, vertex W, let's take some examples, let's take some values. It might make much more sense to you. This edge cost is 1, V to W edge cost is 3, and sorry, 2, and this, let's say this edge cost is 3. When we are adding this particular vertex V to our set X, this is how it looks, and let's call this alpha, node alpha. Whenever we added our vertex V to our new X, because this is cheapest edge 1, so this is the one which is going to be added into our X. This is how it looks. This is V and this is vertex O, let's say. Here is vertex O. This cost is 2 and this cost is 3. Initially, key of alpha was 3 because that is how key was calculated, for every edge crossing the cut. But now, key of alpha is not 3 because the key is defined as the cheapest edge which is incident on it and crossing the cut, and that should be 2. But for this vertex gamma, which was not directly connected to V, the edge cost was 4. Well, it does not change at all because it has nothing to do with whatever has changed in the graph. The only thing that has changed in the graph is the position of V, and hence the only vertices that might be possibly affected by this will be the vertex incident on V. So for vertex gamma, there is nothing to worry about. It's still going to be 4. And therefore, do a local update. Only change those vertices which are in the neighborhood of V. So delete W from heap, recompute key W by doing a minimum computation, minimum of what was the initial key which was previously present, and the all the cost CVW, basically, because if it was only CVW which could have been a candidate, because now this is the only edge which is crossing the cut. I mean, it was previously this edge CVW, sorry, was present in V minus X, but now it's crossing the cut. So if CVW is cheaper than key W, then that will become the new key. Otherwise, key W which was previously present will be the key and reinserted. Basically, it's just one minimum computation. We don't even have to do it for all particular edges crossing the thing. We just have to do it for W, number of vertices W which are incident on V, and we have to do one minimum computation, that is the previous key and the new potential candidate key, and that's it. So what is the running time with this, with heaps? Let's look at that. Running time with heaps. Running time with heaps. Initial n minus 1 inserts. Calculate key for each and every element in the graph except the one which we have chosen to be our starting arbitrary vertex, and initial n minus 1. N minus 1 extract mins. N minus 1 extract minimum at each iteration of while loop. So at each point of time, we are going to insert one vertex in our X at each iteration. Next, each insert, each of these extract mins triggers one insert delete combo. Each edge of a particular insert, each edge of a particular inserted vertex triggers delete, then insert combo, right? By doing by this pseudocode. So each edge VW when V is sucked. So every edge VW when V is sucked into the X, basically when V goes into X, all of edges VW are going through an insert delete combo. So this results in order of M heap operations. That's all. Because there are only M edges, right? Total M edges, and what I'm saying is every edge is going through this heap operation, that is delete and insert. So a total of big O of m heap operations. And what does one heap operation take? One heap operation takes big O of log n time, because there are n number of vertices. So it's a running time of big O of m log n. That's all. So let's think about it. In whenever a vertex v is sucked into our x, we are going to update it. We are going to do a heap operation for each edge which is connected to v. So for every vertex, all of its edges. So the total number of edges is our m. So big O of m heap operations, big O of m times we are going to trigger this delete and insert operation. And for each delete and insert operation combo, it takes a log n amount of time. So it's going to be big O of m log n. That's the running time. So in this video, or in this sequences of video, we have given an algorithm for computing the minimum spanning tree. We have proven that this is a greedy algorithm, and it's indeed the correct algorithm by this part one, part two proof of the cut property and the lemmas. And then we are going to look at we have also looked at the running time of this particular algorithm.